Well, good afternoon, everyone. I am John Mann, Director of Education for Lakeside, and our speaker this afternoon for the Chautauqua Environmental Series is Gil Bohr. Gil has a PhD in Environmental Engineering from Duke University and has a BSc in Biology and an MS in Ecology. He did a postdoctorate at Harvard University Center for the Environment, and he has been a professor at OSU Department of Civil, Environmental, and Geodetic Engineering since 2008. And today's session is Closing the Carbon Budget, Understanding Carbon Flows and Transitions in an Ohio Coastal Wetland. His group has been working in a lake coastal wetland in an estuary of Lake Erie. And this Ohio wetland, Old Woman Creek, has one of the highest methane fluxes ever observed. I would ask if you please mute your cell phone ringers, if you haven't already, and help me in welcoming Gil Bohr.
Thank you for inviting me. We good? Try again. Thank you. Stay away. I don't know. Thank you for inviting me. It's exciting to be here talking about climate change and carbon budget in this wonderful heat wave. Just came back from Germany. The day I left was the hottest recorded day ever in the history of Germany. They had 110 degrees. So let's start with wetland. Let's agree that we all love wetland. And I will tell you why. So wetlands are critically important for water quality. Wetlands typically sit at the edge of rivers and they're interspersed within watersheds. Wetlands are shallow and vegetated, which is the definition of a wetland as opposed to a lake, for example. A lake should be deeper and open water. So by being both shallow and vegetated, the wetlands slow the water down, lead to high rates of sedimentation, both through drag that the plants generate as the water moving through, and by the fact of just being shallow and wide and letting everything that comes in the river sediment and precipitate out of the water column into the wetland. Wetlands are also a wonderful resource for biodiversity. They are a refuge for birds, and you will see some results for sampling that we did in Winers Point Shooting Club just next door to here, which have been maintaining wetlands for more than 100 years for the purpose of maintaining bird biodiversity and maintaining habitats for migratory and resident birds. Wetlands are habitat for amphibians, which again we all love, our frogs and our newts and our salamanders, fish, mollusks, different plants, which are not the usual dryland plants. There are special wetland plants. So we love wetlands. The state of Ohio recognized the role of wetlands in preserving water quality, and the H2 Ohio project is focused on spend tens of millions of dollars to try and improve water quality, especially prevent algal blooms in Lake Erie. And one way to prevent algal blooms in Lake Erie is create more wetlands on the rivers, where river water that carry runoff with high nutrient levels from the field will deposit some of these nutrients, phosphorus and nitrogen specifically, which are used as fertilizer. We need them in the field to grow. We want plants to grow, but then if they go to the lake, the algae start growing there too, and then it's not so good. They grow too much, then they consume all the oxygen, they die, and that's bad. That's stinky, and that's bad for the fish, and sometime on the way of dying, they produce poisons which we don't like to drink. So to prevent that, one way of preventing that, of reducing the nutrient load in the rivers, is by designing wetlands. And all of those purple spots are wetlands in Ohio that's been either created or amended or made better through the H2 Ohio project, which is a very large-scale initiative of wetland design. Wetlands also have another key ecosystem function, which is carbon sequestration, and that's the focus of the talk today. As you can see in that plot, at the top plot, you see how much carbon is stored at different ecosystem types on land. It is separated to above ground and below ground. Wetlands have only below ground component. They store carbon in the wetland sediments. If you notice that the first column is tropical forest, they store most of the carbon in stems of gigantic trees. But again, do the translation, the wetland store slightly more carbon than tropical forest, and this is in total. And this is despite the fact that if you look at the bottom graph, this is the total area in the world, which is wetland, which is much smaller than the total area in the world, which is a tropical forest. Though to be fair, there are a lot of flooded tropical forests, which are both tropical forests and wetlands. So wetlands per unit area are the most concentrated store of carbon. And as an ecosystem, as a terrestrial ecosystem, we're staying out of the ocean carbon cycle. As a terrestrial ecosystem, wetland has the highest role of carbon sequestration. So now why do we care about carbon sequestration so much? This is all about climate change. And we are experiencing global warming. Again, it's not a theory, it's been well observed. Go outside today, but I shouldn't be saying that. This is anecdotally hot. This is not an evidence of climate change. But let's look at the IPCC report. The IPCC is a scientific committee with representative of each country that signed a big treaty for climate change that was initiated in 1979 by the US and participated by almost every country in the world. The US recently left that committee, so we're no longer part of the IPCC. But even before that, you can imagine a room full of scientists from every possible country, each of them with their own interests and their own government on their head, and they need to agree to come to a consensus of what are we sure about. And these figures summarize what they're sure about. They're not making new research, they're summarizing existing observations, existing knowledge. They put this figure in the summary for decision makers, which by their definition should be written to the level of a 7-year-old, so even politicians could read it. And in that table, in this table, the left column is the total observed warming, this gray bar, which is about 1 degree. So, and this is comparing a very specific period from taking the 1850 to 1900 as a baseline. They picked this baseline because there's already quite a lot of meteorological station and collection of temperature data from that period. You can go further back, but then we're making too many guesses about what exactly was before. So taking that as a baseline, that's about 170 years ago, the world on average have warmed by about 1 degree Celsius, which is close to 2 degrees Fahrenheit. And then they attribute what is causing that observed warming. And in the first table, they split it to types of activities. So there is total human influence is just about that 1 degree. Out of the total human influence, that is almost everything. So as you can see, global warming is driven by human influence. So what are humans doing to change the climate? We emit a lot of greenhouse gases. This is the second red column there. And if we only went by the greenhouse gases that we emit, the world has been about 1.5 degrees warmer, so 3 degrees Fahrenheit. But we're also polluting the atmosphere, making the air darker. If anyone's seen The Matrix, that's what you do when you want to shut off the energy, and that's cooling the world. So by air pollution, we are cooling the world. By greenhouse gases, we are warming the world, and this average out not to 1.5 degrees, but to 1 degree of warming. And the next table attributes each of these to the specific mechanism of how it's done. And in this talk, we will focus on the first two columns. So the effect of CO2 is about 0.75, 3/4 of a degrees, or about 1.5 Fahrenheit. And methane is the second to it, which have about half a Celsius, so 1 degree Fahrenheit. So between them, CO2 and methane are making the bulk of the warming due to greenhouse gases. And what we're trying to do in Old Woman Creek is understand the balance between carbon emission, carbon sequestration. As I say, we love wetlands because they sequester carbon. However, wetlands also emit methane. So there's some weird balance between methane emission, which is causing warming, and methane sequestration, which is helping us to fight warming. Put it a little bit in local context. Again, I apologize for showing you a table. It's the worst way to show numbers, but this is how the government provide those. So these are government numbers from GLISA, which is a NOAA-funded branch sitting in Michigan. They have a very interactive website. I have it here, go play. So for the north central Ohio, which is where we are now, the temperature have changed by 2.6 degrees Fahrenheit, or 1.5 degrees Celsius. This is 50% more than that global average that the IPCC published. Why do we have more warming? As you go further north, global warming becomes worse. Around the Arctic, in northern Canada, northern Alaska, they experience a warming of about 4 degrees Celsius, almost 8, 9 Fahrenheit. So we are further than the equator, and therefore we're warming faster. Also cool to notice that we are mostly warming in the winter. Which again, if you think about it, when the whole concept of greenhouse gases was discovered was by a bunch of Swedish scientists at the turn of the 1800s. And in their mind it was a fantastic thing. Who likes the cold in Sweden? So our climate change is mostly hitting us in the winter. Our winters are getting warmer, our summers much less. So the winters warm about twice as much as the summer warm, and the 1.5 degrees is the average. Changing of temperature is not the only aspect of climate. Rain is a very key aspect of climate which we are dependent on. We're dependent on it for our agriculture, but we also need to address it in everything we design, the curvature of the highways, the diameter of the gutters and culverts. These are all designed by rain, characteristic rain criteria. Our rain became about we get about 20% more rain, which is a lot more rain to handle, a lot more runoff from the field, a lot more event that erode the nutrients that the farmer put as fertilizer and pushing them into the river. Not showing in this table, but the 25-year rain, which is kind of a very strong storm event, which is a characteristic threshold in design criteria. If you build any kind of building, develop a plot, you will need to handle the 25-year rain. That became about 30% stronger if you compare it to 70 years ago. I think in the early 90s, the diameter of the gutters in Ohio was increased by 1/4 inch as a regulation because of that. So where do we know all that? So I'm going to take a little tangent with 2 key moments of American science history and 2 American science history heroes. The first scientific evidence that that carbon dioxide is a greenhouse gas that came with the realization of exactly what it will do was in 1856, again, 170 years ago, by Eunice Foote. Now, unfortunately for Eunice Foote, she is of the female persuasion, and therefore she could not present it in the conference because only men scientists were allowed. So she had to give that lecture to a colleague of her who presented it on her behalf, but later publicized the fact that it was originally a study by Eunice Foote. And in that study, she said, the highest effect of the sun rays I have found to be in carbonic acid gas, which is the old style name of CO2. An atmosphere of that would give our Earth high temperature. So she identified the concept of greenhouse gases. Again, they just figured it out, and this is the first she's providing the first measurements to substantiate it. And then she draws the conclusions. And if at one period of its history the air had mixed with it at larger proportion than at present, an increased temperature must have generally resulted. This whole thought of greenhouse gases came from their contemplation of ice ages. The first evidence of different climate in the past was through ice ages. They saw geological evidence of ice ages and said, okay, if the ice was so far, they must have been really cold. Why would the Earth be colder? Climate should have been constant. And this was the first scientific evidence saying, no, there are mechanisms, there are ways by which the Earth's atmosphere can become warmer or colder if we change the concentration of greenhouse gases. About 100 years later, in 1959, almost exactly 100 years, 103 years later, another American hero, Charles Keeling, he was pioneering a new measurement approach, and they just designed an instrument that can measure very quickly the concentration of CO2 in the atmosphere. It was based on a laser light. They calibrated two beams of laser light, one absorbed by water vapor and nitrogen, the other absorbed more by CO2, and by shooting it back and forth between two mirrors and measuring how much of that laser beam have been eaten away, and the ratio of the two laser beams, they could calculate what's the concentration of CO2 molecules relative to air molecules. That was a very big, very finicky machine. All the mirrors had to be cleaned regularly. They deployed some on aeroplanes. They deployed some on Mauna Loa Observatory at the peak of Hawaii, very, very clean, undisturbed oceanic atmosphere. And they discovered a very shocking, Keeling discovered a very, at the time, groundbreaking phenomena. The global concentration of CO2 was fluctuating seasonally, where at the end of the winter it was very high, and at the end of the summer it was very low. And that was evidence that the ecosystem can change, the action of the ecosystem. So Hawaii is at the northern hemisphere, surrounded by ocean, but it's still the air is mixed globally. So the fact that all the North American and European and Asian plants are deciduous in the winter and do not photosynthesize, let the CO2 accumulate. And in the summer where the leaves come on, photosynthesis comes, the plants use sunlight to convert atmospheric CO2 into sugar and absorb CO2 and decrease the global concentration of CO2. Now that was groundbreaking because at the time there was a thought that there is an ecosystem, there's a global homeostasis, there's a buffering of CO2. Whatever we do as humans cannot change the atmospheric concentration of CO2 because atmospheric concentration of CO2 is fixed through diffusion into the ocean and through ecosystem activity. And Keeling showed that that is not the case. So global CO2 concentration is fluctuating and that the ecosystem controls those fluctuations. And he only had 2.5 years of data when he published it. And he prophetically said, when data extend beyond 1 year, average for the second year are higher than the first. So he didn't claim I observed climate change or anything. He was an honest scientist, but he was, if you squint the right way, you can see it. And he was totally right. This is the same observatory. It is still running. It is still collecting information about CO2 and methane and other greenhouse gases. These were added later in the 80s. This observatory was ordered to shut down a few months ago, but Congress, in the great big bill, they actually put earmark of money to keep it running despite the government order to shut it down. So we still get data. This is data that I took yesterday. This is the most up-to-date picture of CO2, and notice that when Keeling measured it, it was at 310. Now it's at about 430, 440. So it increased by more than 50%. What's happening here? Oh, something is wrong here. I'm sorry about that. I don't know where that went. But the flip side of wetland is they produce a lot of methane. I had a beautiful figure here with a global attribution of methane to different processes with a yellow highlight of the role of wetland. The take-home message, let's go back to a nice, more elegant picture, but the take-home message here is that wetlands are the largest natural source of methane. The amount of methane emitted by wetlands is about as much as methane emitted by human activity. And we use methane, this is our heating gas. So we emit a lot of methane, either through agriculture, through belching of cows and sheep, or through emissions from any kind of oil and gas extraction operation. Some methane will leak. If you know the big flares they have, they're trying to burn the methane away, but again, it doesn't burn all of it. Also, wetlands are the largest source of uncertainty. So we're not sure. The methane is much harder to measure than CO2. And it's the laser that can do that was developed only 20 years ago, not in the 60s. And there is a lot of the uncertainty of how much methane exactly is being emitted by what, or globally, is very large relative to CO2. And the highest source of uncertainty is wetland. We don't know what wetland do plus minus 150%. And so the need to understand how wetland, to kind of come up with a modeling approach, to be able to know globally. You cannot measure methane at every point on Earth. So the only way to go is we can see from satellites where wetlands are. We can see from satellite what's the methane concentration mixed in the atmosphere. But to know how much methane comes from each wetland, we need to go wetland by wetland, understand what makes it work, understand the conditions that determine how much methane is being emitted from a few measurements that we have, and then extend it globally through a model that's constrained, so it cannot produce more than what we see the total, but it has to produce at least that. And our best attempt so far converged to about 30%. So if we try to model up all the wetland and mix them up, we get about 30% less methane than what we see from satellites in the atmosphere. This is known as the bottom-up, top-down mismatch. And my work is strongly in the context of trying to close this mismatch by understanding wetlands better. So why is it hard to understand wetlands? Because wetlands are complicated. Why are they complicated? They combine soil and water and plants. All of them interact in unique and interesting ways. So a very simplistic way to look at it is wetlands are never, even swimming pools have a depth gradient. So they're not like dug, they are rarely flat dug ponds. So we have some depth gradient. And as we have depth gradient, each depth layer, each area of different depth will have different characteristic vegetation. So the very shallow part that's slightly popping above the water would typically have reeds or tall grass. We have a mud flat that's fluctuating between flooded and non-flooded, and that's usually bare. We have then cattail or emergent vegetation that can pop up above the water, but they don't like to put the roots too deep. Deeper, we have floating leaf vegetation like water lilies and lotuses. And deeper than that, you will again have open water with submerged vegetation below that. So we need to understand how hydrology interact with the biology and how they all affect the carbon-methane relationships. Here is the wetland that will be the focus of the talk, Old Woman Creek, nice little picture, just to show you that every wetland, even small, even straight up wetland, conservation wetland, is heterogeneous and has complexity. So again, typical picture of Old Woman Creek, and now notice the dark green is cattails, lighter yellow is lotuses, and the in-between is lilies, and then the blue is areas of open water, each of them doing something else. Other things that gets very complicated with wetland, I will not go through that at all, but unlike photosynthesis, which is that big green circle which CO2 comes in, the plant photosynthesizes it and turn it to sugar. Not a super straight up process, but done by one ecological unit, plants, in a way that's easy to reduce when you are modeling it. Whereas the methane pathway is very, very complex and involves interaction between fungi, which is doing the fermentation, and bacteria, which is doing anaerobic fermentation. So for example, you all know fungi fermentation in the yeast. When you make sourdough bread, that's you using a fungi to ferment your carbohydrates, your starch in the bread. You all understand microbial fermentation in the process to make yogurt. Again, you are taking a carbohydrate, the milk sugars, using now a microbe under anaerobic condition without oxygen to turn it. That's why it turns kind of sour. It turns it to organic acid. Once we took the plant-produced carbohydrates and fermented them into smaller sugars, then other archaea, and archaea is kind of like, they are kind of microbes, they're kind of like bacteria, but there's something completely different branch of the tree of life, so animals are as different from plants as bacteria are different from archaea. Totally different creatures, but microscopic as well. They can work in anaerobic environments without oxygen, and take those simple sugars and produce other things from them. One of them is methane. If you go back to areas which have oxygen, everyone is breathing. So the process of breathing is basically controlled explosion. We are burning things by our breath. Bacteria breathe, plant breathe, animal breathe. Everything that consumes sugars is by the process of breathing, turning those sugars back into CO2. And some microbes can take methane and breathe, basically burn the methane and turn that into CO2. So we have this very complicated, plants make CO2, and now fungi, bacteria, archaea of different kind is doing different things with it, which purpose of telling you all that is for you to appreciate the complexity. So when someone will complain that our scientists don't understand anything and our models are silly, understand that we're doing our best. It's hard. Next thing that makes it hard is how these things move around. So I said the plants are making CO2, but they do that in the leaf, above the ground, or in the water column. But then that sugars, that plant material need to move into the soil. Top of the soil is aerobic. As you go deeper, there's no oxygen, it's anaerobic. So as the carbon is moving around, it's being exposed to different processes. Now, in the wetland sediments underground, we have production of both CO2 through breathing and methane through methanogenesis, the process of anaerobic turning sugars into methane. Now, the question is, what happens to that CO2 or methane? Does it move back to the air, or does it stay in the ground? If it stays in the ground, we are happy. We call it carbon sequestration, go wetlands. If it's moved back to the air, it kind of cancels out the photosynthesis. And we tend to count, we call a process called net ecosystem exchange. NE is the net. There's how much plants uptake with photosynthesis, how much is emitted back in the process of breathing, and the net is the carbon that typically tends to stay in the ground. But then some of it became methane, and if the methane stays in the ground, it wouldn't bother us at all, but the methane tend to move up. And it can either diffuse through the soil and the water column, which is a relatively slow process. As it's moving through the water, because of wind, is mixing and has oxygen in it. So now it can be breathed away and turned from methane to CO2, which is better, it's less of a greenhouse gas. One molecule of methane absorbs infrared radiation about 200 times more than CO2. But then CO2 is forever, and methane tends to be breathed into CO2 and will convert to CO2 with time. So usually they work on a 100-year. So in a 100-year, 99% of the methane, if you just keep it in a balloon, in an open box, and follow the same methane around, after 100 years, 99% of that methane would have turned to CO2. And if you count how much more greenhouse effect that will have, and there's a lot of arguments about it, depends what elevation and so on, how much water vapor was around, somewhere between 25 and 38 times more effective. So we are happy with our methane turning to CO2 in the water column, but one way to shoot out straight into the air is to go through the stems of plants. Most wetland plants cannot breathe. The roots of wetland plants are stuck in anaerobic soil and cannot breathe. The way around that is that wetland plants develop a special tissue called parenchyma, which is basically like straws. If you ever cut like a stem of cattail, you see it's kind of very porous, very straw-like tissue. And air is moving down that straw into the roots, but then the same straw can let the methane a straight way out. So we need to understand all of that when we do our models of how much carbon is turning to methane, back to carbon, or staying in the ground. So now let's go to, this was theory, introduction finished. Let's go to the real world. Old Woman Creek, it's a National Estuarine Research Reserve, NER. The NER system is a system funded by NOAA. It's a national system. Every state with a coast should have a NER. Most of them have, not all of them do. There's about 30 NER centers around the country. The one in Ohio is in Old Woman Creek, which is just next to Huron, Ohio, very, very close to here. It is run by the Ohio Department of Natural Resources, which are doing a fantastic job of outreach and activities and research, and they are extraordinarily welcoming and fun to work with, and I recommend each of you to visit that fantastic site. Here's a satellite image of Old Woman Creek. So my tower, my measurements are done at that point here. The visitor center is up here, Lake Erie is here, and here is the mouth of the wetland. So this is, Old Woman Creek is a river. The entry is here. This is the railroad. This is route number 6. And here is the mouth of the wetland. And just to make things, I just finished explaining how difficult wetlands are to work with, how complicated they are because they have different depths, different vegetation, crazy pathways of microbial activity, and crazy, strange pathways of moving in and out of the soil. Now we have also a dynamic complexion. So the hydrology is changing in time. And in Old Woman Creek, the hydrology is changing in time in more than one way. So the most drastic way is that barrier at the mouth of the wetland. So the reason that this place is a wetland and not just a straight up estuary flowing into the lake is that the lake deposits a sand dune, which you can see here, that's blocking the mouth of Old Woman Creek of the river. And when that sand dune is accumulated, the wetland is growing behind it. And it can be about 6 to 10 feet higher than the lake elevation. And then comes a storm, too much water overruns the sand dune, which acts as a levee, erode it away, and you see here it's open, and then the whole wetland empties out to the lake and become very shallow and equal to the lake level. The lake level itself is changing. And I don't know if any of you owns a lakeside property, you will know that Lake Erie peaked in 2022 at a level that's about 3 feet taller than what it was 10 years prior to that. There was a lot of coastal erosion, lots of talk about stabilizing the shoreline, and now it's going back down. And as you can see here, this is 1 year, from 2023 to 2024. There's also a seasonal cycle. Lake Erie is much lower in the winter and much deeper in the summer. And by much, I mean a few feet difference, but a few feet is a lot for a wetland. Blue line is Lake Erie. Green line is the wetland, Old Woman Creek. Old Woman Creek, when the barrier is open, every place where there's a white background, the wetland is at the same elevation as the lake. When the barrier is closed, and the blue line here is when it's closed, the wetland starts climbing up, kind of stabilized behind the barrier. Then comes a storm, a lot of rain, very quickly rising, toppling the barrier. Red line is barrier break, everything empty back to the lake level. So now we need to understand all of that to know the depth, because we need to understand the depth because we need to know how things are moving from the soil to the ground and what plants are where. But we figured it out, mostly through the work of Parisa over there, my student. She did the hydrology. And now I'm showing it last, but this is the motivation of the research. So some years ago, a colleague of mine from Berkeley Lab made an intercomparison of all the sites that reported methane measurements using the eddy covariance technique, which I will talk about shortly. And this is Old Woman Creek. And this, notice, is a logarithmic scale. So it's about 100 times more. So this line is what you would expect by the mean average temperature. So tropical wetlands emit more methane, Arctic wetlands emit very little. It's cold, bacteria don't like it cold. That's why we put our food in the fridge, so it will preserve. Bacteria don't like it. But for the typical temperature of northern Ohio, we emit about 100 times more than we should. And for the first few times I tried to report my methane data, it was rejected. They kept saying I'm using the wrong units. I was measuring, they were expecting tens of nano, and I was giving them micrograms of methane.
I'm going to take this paddle and really
So
stir
how
up
much
the
methane
soil.
is
It's
there?
gonna
Show a
release
little
lot of bubbles of
demonstration.
methane. We're going to trap them in here, and then we're going to uncap it and light it, and it's going to make a big flame all at once.
Nice.
So you can see all these bubbles. That's a lot of greenhouse gases coming up. Hopefully a lot of it's methane.
Let's light them up.
Okay, so we're going to try this now.
And they all left that day without eyebrows. And it's good that me, the supervisor, wasn't there. The two of them, the guy that was talking is Tim Morin. He's a professor in SUNY ESF, again, not far from here. This guy here is Camilo Rey Sanchez. He's now a professor in NC State University. And this is in a demo for kind of a kids blog, kids online blog called Aqua Kids. So there is a lot of methane in Old Woman Creek. And we want to understand why. So just for you to know that Old Woman Creek is not the only methane criminal in the world, it's just the only one that we monitor regularly with eddy covariance. So eddy covariance technique is measuring all the time. It's a tower, it's measuring the methane, it's measuring the concentration at very high frequency, and it's measuring the wind speed at very high frequency. So we're basically counting how many molecules move up, how many molecules move down, calculate the difference, we know how much methane moved up to the air. But you can use other techniques to measure methane, like chamber accumulation, and they are much harder to work. It's not a sensor that you leave there and start logging the data. You need to go there with the chamber, you need to be there and do the work. So you measure every once a month, maybe. And if you notice all the dark sites, these are two sites in the prairie potholes. I don't know where this one is, this one somewhere in Sweden. There are other sites that emit as much methane as Old Woman Creek or more, and as was noticed with the chamber measurements technique. And all of these sites share a common characteristic, and all of them are in an agricultural watershed. So something to do with being in an agricultural watershed, which is typically the high nutrient concentration, which technically should not affect methane production, but we're trying to figure out what's the connection. So if you look, this is the same plot with the temperature prediction line. Old Woman Creek is an outlier, but here there's few other sites which are measured by chambers, which you can see are about as high. This is a new plot where nothing is jumping above the curve. In this curve, they took the difference from the temperature prediction, and they correlated that difference with how much of methane generating archaea, specific ones, are in the mud. So it's not an explanation, it's just showing the characteristic. What is different? These sites have so much methane, and it's really in the methane production. There's all this methane producing archaea in the sediments, and the more of those bacteria we get there, the more methane emission we have. But we still need to understand what's special in those sites that have so many of those. And I'm telling you already now, I do not know the answer. Don't be disappointed in about 20 minutes when I didn't get there yet. So we threw everything that the government was willing to pay us to study and understand it. So we ran measurements, we call it a multi-scale campaign. So we have this eddy covariance tower. Where is that? So here is that machine that measures with a laser. We measure the concentration of methane, very high frequency. We measure the wind at very high frequency. We know how much go up, go down. Said before, this is a chamber. You put it on the water. You measure the concentration of methane and CO2 inside the chamber. And as the methane kind of moves out of the water to the air, because the chamber is closed, the concentration increase. We can then calculate from the rate of increase how much methane went to the air. And then we took soil cores, which are kind of disturbing we extract soil cores, we poke the soil, take out the core and look what's in it, and we left peepers, which are kind of little fixed observatory that go into the soil, allow us to measure different levels within the soil. So here's some temporal retrospective. The data that you saw with Old Woman Creek being the craziest in the world was done with the data of the first 2 years. Since then, we had 10 years of measurements. Out of them, we actually managed to measure only 5 because it's hard. Water keeps moving our tower. We don't have power there, it's all solar, we lose power all the time. Ice is dragging the station in the winter. There was a move from LTE to 5G, which then we lost data connectivity for about a year, all kinds of reasons. So these are my lame excuses for that gap here. But notice that methane flux was much higher in the first 2 years and much less in the later years. And we kind of noticed that the earlier years were shallower and the later years were the years when Lake Erie peaked, so they were deeper. And everything that I've told you so far say we need anaerobic condition in the soil, so lots of water, so the oxygen doesn't make it to the soil. Common wisdom is the more water you have, the less oxygen you have, the more methane you have. And I'm showing you the exact opposite. More water, less methane. Why? So one thing we realized working at the edge of the wetland is that the water depth is working as a switch. So if the water is just below the soil or just above the soil, there's very little methane flux, and actually there's a source of CO2. As the water gets deeper, we have wetland plants developing, then they uptake CO2, and the methane flux become higher. But it doesn't matter how deep, it's just the difference between not flooded at all and flooded. So if you have the water above the surface, high flux, water just at the surface or below it, there's low methane flux. But then as you start getting deeper and deeper and deeper, we are reversing that dynamic. So relative to at the surface, adding more water will add a lot of flux. But then if we keep adding water, now we're changing it to something lower. And here's the time series of the water table depth of the water elevation of the wetland. This is a baseline of where we built the tower in 2015, that dashed line. And you see we built the tower was actually on a mud flat, not in a flooded. Now it's in a completely permanently flooded. You need to canoe to the tower, which makes work even harder. And we develop a remote sensing approach to look at satellite image of the wetland and know which type of plants were everywhere. And you see that in those 5 years, the wetland changed completely. As it got deeper, it switched from Taifa-dominated, tall cattails, a lot of carbon uptake, a lot of methane emissions, to mostly lotus, which somehow emits less methane, definitely uptake less carbon. Things to pay attention is the concept of a flux footprint. What do I mean? What do we measure? So where do we measure? So my tower is here, but I have this sensor that's basically measuring methane in the wind. So the question is not where we measure it, but we want to know how much methane went up to the air from the wetland. The question is, where did that methane come from? And we can calculate based on the wind direction and wind speed, where is that? And that can change. So sometimes we can get it from the open water, sometimes from the Taifa. But as in the first 2 years, we were mostly getting fluxes from Taifa. After that, the Taifa disappeared, and we were mostly getting fluxes from open water and lotus. And each of those patch types have, and this we did with chambers. So in chambers, you can put your chamber on a spot and know exactly what came from that spot. Whereas in the tower, you get this mixture over this bubble. So we know that open water emit the least methane, lotus and lily less, and cattail the most. Now the question is why? So we have those leaf chambers. Here's that parenchyma tissue I was talking about, the tissue that the plants evolved to move oxygen to the roots so they can breathe, but the methane is abusing to get out. And if we close this very sophisticated Walmart tapestry chamber over a bunch of leaf and measure the change of concentration inside, so give it some time, this is in seconds, so that's 2 minutes, methane concentration increase. This is transparent, so there's light to the leaf, so CO2 concentration decreases, they photosynthesize, and we can measure exactly what's the rate of CO2 uptake and what's the rate of methane emission by different plants. And if you normalize it you can normalize it by leaf area or by ground area. Cattle have much more leaf area than lotus and lily. Lotus and lily don't go beyond 1 because then they start overlapping each other, whereas cattle can grow to about 2 or 3 a lot of leaf per unit ground. And per ground area, the cattail transport the most methane through its branches. But that's not the whole story. There's other ways for methane to come out. So for chamber in the water, we measure the diffusion, and this is a chamber we left on the water, and you slowly see methane concentration accumulate. That's how much diffused through the water. But then methane can get so strongly concentrated in the ground so it can bubble out. You saw these bubbles when Tim was mixing the mud. And typically, when you measure methane, if you have a bubble in your chamber, you throw the chamber data away because science couldn't handle that. So if you want to fit the red line to this, that doesn't fit. And we develop an analysis technique to identify kind of AI approach to find those jumps due to the bubbles, and we can then subtract the jump to get the red line to fit, but then we also know how much we subtracted, so we know what came with the bubbles. So this is how much came out with bubbling. And if it was about, so previous slide that looked exactly the same was almost there to convince you that because of high conductance through the leaf, there's a lot of leaf area, a lot of parenchyma, a lot of methane is moving through the plants. Great, very convincing, cattle is the most methane. But if that was true, methane that was moving through the plant was coming, if there was the same amount of methane produced in the soil and more of it coming through the ground, through the plant, less of it would bubble. And we actually see the opposite. It's exactly the plants that move more through the plant are also bubbling more. So it must be about production. Those plants are producing more methane. So the bacteria living in the roots of those plants are producing more methane, probably because those plants photosynthesize more and feed them with more sugar. So kind of as a graphic summary of what we see, a lot of things are happening with the water elevation change. And we know the water elevation increase. We know bubbling, the role of bubbling change, not clear how. It's kind of opposite than what we expected. But now that the water is deeper, the methane, either that diffuse or that bubble through the water, need to spend more time in the water. Water is aerobic, so bacteria are eating it away. Production stayed more or less the same. So with more water elevation, again, it's a switch. If the water is deep enough, doesn't matter how deep, methane is produced about the same amount. But when it's a very deep water column, on its way out, the methane is being breathed away and turned into CO2. So we see less methane from deep wetland. And that's an important conclusion about wetland management. So we are building all these wetlands to control water quality. I know it's not a government priority right now, but we can think about our design of those wetlands, especially the hydrological management of those wetlands, in a way that will help us also maximize the climate change impact of the wetlands. So minimize the methane emission by keeping the water elevation high, while allowing wetland plants to grow to photosynthesize more. And this is the fun of soil core extraction, very elaborate work. Here's the soil core. This came out of the soil. We can then push it out and cut it to slices, to little cookies, we call them. And we can then analyze the concentration of carbon, nitrogen, phosphorus in the cookie and kind of get the vertical profile of that. Whoops. What's happening to me? I'm going the wrong way. The other thing, we can use lead analysis. So radioactive lead was put in the air by nuclear open air nuclear test explosions that ended in the 50s. So we can measure in the deposited soil what's the radioactive lead concentration and kind of know how old that soil is. So if we know for each cookie how much carbon and when it was deposited, from the difference between time, in the time difference between the cookies, we can calculate how much carbon accumulates. So we can translate this vertical profile of carbon concentration, which has been dated, to a measurement of carbon sequestration rate, how much carbon entered the soil per year. Now I want to go forward and I cannot. And again, wetland complexity. If you go near the mouth of the wetland or near the river entry of the wetland, you get different concentration rates. If you look at shallow, intermediate, or deep water, you get different concentration rate. We cannot put here the profile under Taifa versus profile under Lotus because they change every year. And this is a very long-term course. So every cookie is about 2 to 5 years. So this is going 30 to 50 years back. We extended that with the help of the Winers Point people to a whole bunch of wetlands kind of around here. Took the same soil core from every wetland. And look, here is example, very, very different, very heterogeneous, different wetland type, different cover, different depth, different hydrologic management. Here you see the brave students doing the heartbreaking work. Of course, it was a heat wave that week too. It's always a heat wave when you do field work. And you see that each wetland, this is the carbon sequestration. Up here, nitrogen and phosphorus. Take-home message of that is two. One, every wetland is different. There's huge differences between wetlands. This is not an easy and simple picture as we thought it will be, that every color will have a characteristic. So every color is a type of wetland, type of hydrological management of wetland. Our hypothesis was that by the hydrological management, again, everything that I show you so far should tell you that by the way the hydrology of the wetland is handled, you should expect we'll control the sequestration rate. Not that simple. Other hypothesis is that the date where the wetland was amended, is it a 100-year-old wetland or a 2-year-old wetland? That has an impact, but not on the recent 10 years. So every wetland is different, doing its own thing, but then one thing to notice is that there's almost perfect correlation between carbon, nitrogen, and phosphorus. And they're coming from completely different processes. Nitrogen is a mix of fertilizer and microbial activity. Phosphorus is pure fertilizer, and carbon is pure microbial activity and plant photosynthesis. The only reason they are all looking the same way is that the only thing that controls them is the hydrology. So they all share a common hydrology. The wetland is deep, the wetland is shallow. When it's deep for the carbon, it's deep for the nitrogen, it's deep for the phosphorus. Everything else is different for each of them. So we still really believe in this hydrological control. It's just more complicated than just the name that we give the control. To go through two examples, this is one side, Metzger Gate in Winers Point. That side was farm until 2010 up here, and then became a marsh to support ducks in 2025, and you see a huge spike in the rate of carbon sequestration that comes with a huge spike in nitrogen and phosphorus accumulation. This was done with the H2 Ohio project, and our data show it's extremely successful. All of this nitrogen and phosphorus are now in the soil of Metzger Gate and not in Lake Erie. And at the same time, they're sequestering a lot of carbon. Fantastic. Here's a different side that looks much weirder, but look at the scale. This is 1 to 100. This was 1 to 50. So this site became a wetland in the 1920s, before our dating techniques can even get. So it was always sequestering a lot of everything. But then the way they managed the hydrology, it was relatively drained most of the time. It was very briefly seasonal from the 20s for 100 years until 2020, from 1920 till 2020. Then in 2021, they changed the way they managed the water, and they let it flood much more often and flood much deeper. And again, sequestration rate shot up of nutrients and carbon. So maintain your wetlands deeper will have a huge benefit. And even though we don't understand everything perfectly, we took everything that we do know, put it in one of the world's most sophisticated Earth system models. The Earth system model had an embarrassingly silly way of representing wetlands. They didn't even represent wetlands. They say whenever we identify there is water in the soil, we operate a methane production module, but there's no wetland plants there, there's no inundation depth. Nothing that's important to characterizing a wetland wasn't part of that model. So we changed it. And the model is called ELM, which is the Earth, is the E3 is the energy, Energy Exascale Earth System Model, E3SM, is the model of the Department of Energy, is one of the 3 official participants of the US in the IPCC Future Climate Projection Project. There's the NSF model, the DOE model, and the NOAA model. This is the DOE model. And this is the land model component of that model, and we called our little variant of it ELM wet because it had this special wetland. The model represents different land units with different processes in them. We added the wetland. And we were very proud of what we did, and we thought we're going to get, finally someone can simulate Old Woman Creek. No, terrible. Couldn't even show it in the project report. We are way off, still way off. So now, why are we way off? So one thing we noticed from our sampling in all the wetlands around Ohio from the soil core, we see a very, very tight correlation between total dissolved nitrogen and total dissolved organic carbon. So there's a component in the carbon cycle that I haven't even mentioned yet. Kept saying there's photosynthesis, the plants are putting carbon, making sugars, sugar gets fermented, becomes methane, then get breathed out. But there's all this CO, there's all this carbon, all the sugars that are coming down the river. And those sugars are coming not alone, they're coming with nutrients. So there's nitrogen and carbon coming down the river. And we are strongly suspicious that this is why wetlands in agricultural watersheds specifically have such high methane emission. One, because there's all this extra sugar coming in, and methane is made of sugar, so it's not only what the plant are photosynthesizing. And 2, maybe nitrogen is maybe spiking it further up. We are further away from understanding the nitrogen aspects of things, but we more or less pin down the carbon aspects of things. So for you to get the ballpark numbers, this is how much carbon gets in the wetland sediments by photosynthesis. About 100. Doesn't matter the units. This is how much comes down the river. About 60% more than that. So it's really more about what comes down the river than what is being processed locally by the plants. Now, methane flux, common wisdom say that methane flux should be 3 to 5% of that. Our methane flux is 25% of that. But it's only 7% of the total if you add those two together. So it kind of makes sense. There is high but not insanely unreasonable 100 times too high methane emission if you account for the carbon that comes in. Sequestration that should be equal to this minus that is actually much smaller than expected. And then there's a lot of carbon that just, whatever is left is moving down the river. And as an honest scientist, I have to tell you that 62, this is a model, and we have measurements to generate each of those errors, but measurements have errors. And this is the sum of all of my errors, which is quite, which is quite large. It's about as large, it's 2/3 of the photosynthesis is about a half of the DOC inflow. It's twice as much of carbon sequestration. So put things in context. I admit, I don't understand everything, but we're getting closer than the beginning of the talk. And just to finish on an optimistic note, our model is not crap. Our model is fantastic. When it's working easier, more normal sites like the wetlands in Louisiana, we're getting fantastic results. And let's go through this complicated curve. The red line is the model before we touched it. The purple is the observation. As you can see, the red line is doing crazy things compared to the observation, has no clue. It's going down when it should go up, going up when it should go down, quite far from the observation. The green is our model, perfect. I will accept nothing less than that. And the cool thing about being perfect, it's perfect in very, very difficult times. So this was a short drought, which is very challenging to model, followed by a hurricane storm surge of Hurricane Ida. And even though we did not tell the model this was we prescribed the hydrology, but the hurricane didn't directly was imposed on the methane production, it created a very, very realistic pattern. So really, we are almost there. We understand what the hydrology is doing. We are now on the way of getting this dissolved organic carbon coming downstream, and we think that once we incorporated that, we could really understand what's creating very high methane emission in productive wetlands. And I will end here on this optimistic note. Hope you are optimistic about science as much as I am. Thank you.
Question.
Questions? Yes.
So for the New Orleans watershed, that's a non-agricultural watershed?
Less. There is nothing
Less.
non-agricultural in the world by this point, but less.
Okay, thank you.
And I don't actually know the numbers, but the concentration of nitrogen in the water is much lower, and the concentration of organic carbon in the water is much lower.
Okay,
That I can tell for sure.
okay, thank you.
Yes.
Well, you're right here, I guess I can ask you.
You want them to hear.
Do you by any chance know what the little rafts are that are in the Sandusky Bay and down the Sandusky River? I haven't been there this year, but the last couple of years they've looked like some kind of inspection things.
I do not know. And we did not work there's another group that's studying wetlands that work in the Sandusky Bay. They're funded directly by the Department of Energy with professors from University of Toledo. Inca is one of my co-authors. We work together in my wetland, but she's working with the DOE team at the Sandusky River. Maybe it's their thing, maybe it's something else. I do not have knowledge. The wetland we worked at were around the bay, were mostly the terrestrial wetland, not the bay itself.
Well, there was a rumor at the local bar on the Sandusky River that they were counting fish.
Seems very reasonable thing to do, I don't know. There's a lot of money invested in fish stocking around here. I would imagine someone in the government wanted to know if it's effective or not.
So would you say again that that there's still too much nitrogen that's been used on crops that's going into the river?
So too much is judgmental. I can report the numbers, I can't tell you what's too or less much. That's one. And the other thing, I have no knowledge about what is needed on the field. My scientific vision is very narrow to what's in the wetland. What I know is that both the organic carbon, nitrogen, and phosphorus concentration in the water that's coming to Old Woman Creek are very high. And in many of the other wetlands that we sample in Ohio, it's again very high. And we did not see a direct correlation between those instantaneous concentration in the water and emission. We think it's more long-term of what makes it to the soil and gets fermented. We do know, again, anecdotal knowledge that the highest emitting wetlands are all in agricultural watersheds. And again, I don't want to throw shade at farmers at all. I did not study anything there. What I can tell you is that wetlands are very, very effective at sequestering those nutrients. So if you were to help the farmers, or if the farmers wanted to amend some of the consequence of what they're doing, they could allow a very small fraction of the land to be wetland, and that very small fraction of land that's reserved as a wetland, if maintained hydrologically flooded, can go an extremely long way in terms of absorbing nitrogen and phosphorus out of the watershed.
Thank you very much, Gil. Thank you.